So here are a couple problems that involve simplifying expressions that involve composition of trig and inverse trig functions that don't necessarily cancel each other perfectly, where we're going to expect an expression involving variables within our answers. So this is something that you work with a little bit in trig, pre-calculus, and then if you are taking derivatives of inverse trig functions, you have to do a little bit more of this sort of simplification then. So what I wanted to do was take tangent of arc cosine, and arc cosine is the same as inverse cosine, so tangent of arc cosine of x over 7. So what I wanted to start with here is I wanted to figure out what exactly is inside this tangent function. So I kind of said, let's take arc cosine of x over 7 out of the tangent function, and let's call that theta. Right? We put angles into the normal trig function. So I said, let's define theta to be arc cosine of x over 7 or inverse cosine of x over 7. I then said, well, I would personally rather deal with normal trig functions as opposed to inverses. So I took the cosine of the left side of this equation, took the cosine of the right side of this equation. Cosine and inverse cosine do cancel because they're inverses of each other. And then on the other side, I end up with cosine of theta. So what I know about this line right here is that I have cosine of theta equal to some fraction. And I know from SOHCAHTOA that cosine of an angle is equal to the leg adjacent to that angle divided by the hypotenuse of the right triangle. So this line right here actually allows me to draw a triangle. So I'm just going to draw a triangle. I am going to draw a right triangle because if I'm using a piece of SOHCAHTOA, it only applies to a right triangle. So I just called the angle theta, the angle in the lower left. I didn't have to do that. I could have put it anywhere. You just have to make sure you label everything else appropriately. So cosine of theta is adjacent over hypotenuse. Cosine of theta is equal to x over 7. So I knew I wanted to label the side adjacent to theta with an x, what I see within this numerator. And I wanted to label the hypotenuse of that triangle with a 7, since that's what I see in the denominator of what cosine of theta is equal to. I now know two of the three sides of a right triangle. I can use the Pythagorean Theorem to get the third. So I'm just thinking of this as a, b, and c. So if I do a squared plus b squared, that's got to equal the hypotenuse squared. Well, I want to solve this for b. So I can subtract x squared from 49. I can take the square root in order to solve for b. If you think about what we really wanted at the onset of this, it was tangent of what we've been working with for the past few minutes. We defined what's inside that tangent function as theta. So the original problem really says, hey, what's tangent of theta? Well, now that we have this right triangle drawn, all the sides are known, and theta is in the lower left, we can recognize the tangent is equal to opposite over adjacent from SOHCAHTOA, and opposite from the angle theta, we have this value for b that we found, that square root of 49 minus x squared, and then adjacent is what we divide by when we evaluate a tangent ratio from SOHCAHTOA, and adjacent to the angle theta we see x. So the original expression, which really is tangent of theta, is equal to the square root of 49 minus x squared over x. We have another one over here that we can talk about for a minute or two. We're going to take the exact same approach. So we're going to focus on what's inside the trig function first. Normally we put angles inside of trig functions. So I'm going to define what's inside this trig function to be equal to theta. So inverse sine of 3 over x is equal to theta. Just like we said on the opposite side of the screen, we would rather deal with normal trig functions than the inverse trig functions. So sine and inverse sine, when I apply them to each other, they cancel. So I'm just left with 3 over x on the left, and I'm going to have sine of theta on the right. We have sine of theta equal to a fraction. From SOHCAHTOA, we know sine is equal to opposite over hypotenuse. So if I draw a triangle, put theta in somewhere within that right triangle again, I can recognize that sine is equal to opposite. So opposite the angle theta, I put a 3 divided by hypotenuse. So on the hypotenuse of the right triangle, I put an x. Once again, we know two of the three sides. We can do Pythagorean Theorem to get the third side. So a squared plus b squared has to equal c squared. So a squared plus 3 squared has to equal x squared. What does a equal? We'll subtract 9 from x squared, take a square root, and you know that a has to equal to the square root that's written here. What did we really want to simplify? Well, we wanted to simplify cosine of the expression that we've been working with for the past few minutes, which we defined as theta. So cosine of theta is really going to be the answer to this problem, and cosine of theta, according to the triangle that we just built that contains theta, is got to be equal to adjacent divided by hypotenuse. Adjacent to the angle theta, we have a, so that's the square root that we just found, and then we have to divide by the hypotenuse, which is x.